evaluate the pressure and velocity limits. Okay, we need to make sure that it does not exceed the material limit. These are the material limits. So we're first going to evaluate Pmax. And this is the formula. I spare you the derivation of the formula. So F is the radial load, D is the diameter, and whenever we talk diameter, we talk about the inner diameter, because that's the interaction between the shaft and the bushing. Okay? So we have 4.58 megapascal. Pascal is Newton per meter square. So megapascal, 10 to the 6. Now we have the limit here for SP500 oilless is a brass bushing. The limit is 24.5 megapascal. So this is less than 24.5. Means it's okay. That's a material limit. Beyond that, you're gonna destroy the material. So V, maximum V is pi Vn. So this is the velocity of the shaft at the surface. Meters per second. Again, if you think about the bushing, if I open it up, it becomes a rectangle just like this table, and the shaft actually flies on this, right? And this is the velocity. So the shaft rotates, and so if you open it up, the material interaction is like a linear rubbing, and that's the velocity of the rub. They have a limit of 0.51, so this is also okay. It's still under that limit. Finally, we have PV. So whenever you're selecting or evaluating a bushing, these are the first three things you evaluate other than wear and temperature. That's a formula, so you have pi, 2250, and then multiply by n. However, n we're given as 200 RPM, and we need to do everything in SI units. So it's 200 RPM converted into seconds. How do you do this? Multiply or divide by 60. Our revolution per minute, you want revolution per second. Okay, my conversion style is always, I want to change minutes into seconds, right? Yeah. So I put minutes on the top so I can scratch it out, and seconds on the bottom, because where I want revolution per second, there are 60 seconds in 1 minute. That's how I think about it. If you are ever confused, that's my suggestion, do that. Write down and scratch things out. Okay? So we have 0.942 10 to the 6, or I'll replace it as MPa, meters per second, is the unit of PV. And the limit is 1.64. This is less than 1.64, so this is also okay. Alright, so these are the PV limits that you have to evaluate. Next, we're going to do a wear evaluation. The question is, when will it reach that? So wear calculation. The formula is there are two formulas. If you look at my slides, the original formula is given as the wear, W, okay? W here is wear. There's also time, T. So the time it takes to reach this wear. But you can rearrange this to get T. Okay? So that's just, well, there it is. I did it. So we are going to evaluate T because that's what we want is the time. So it's the wear limit multiplied by L divided by 4, F1, F2, K, Fn. Now, let's talk about F1 and F2. F1 is determined by a lookup table. F1 is the motion related factor, and F2 is the environmental factor. Okay? So this is how you look up F1. F1 is evaluated based on the average pressure and velocity and the type of motion. Okay? So in order to determine F1, we're going to have to do a quick calculation. I'll just erase this. So in order to do F1, we need average pressure. And average pressure formula is F divided by dl. Not the maximum pressure, this is the average pressure. It's 2250 divided by 0.025, 0.025, 3.6 megapascal. Okay? Our motion, what is our motion? Okay, so it's just a rotation, right? It's a rotary. So if you look at this, the mode of motion is rotary, not oscillatory. Oscillation means back and forth, right? And then you have reciprocating, also going axial. So this is rotary. Velocity, what's our velocity? Velocity is 0.262. So what is it in millimeters per second? Huh? 262 millimeter per second, right? Yes. Rotary and pressure average. So rotary and my pressure is 3.6, so it's 5 or less. And we are in this range of velocity. So our F1 is ranging from 1.3 to 1.8. There. Okay, so we are here. Rotary, P is less than 5. Velocity is in this range, so my F1 is in this range. And so you ask, what's your next question? What is my F1? Well, it's in that range. So which one is it? And I'm sure at this point, many of you felt like, is it 1.3 or is it 1.8? Well, welcome to engineering. There's a difference between science and engineering, okay? Engineering, we estimate. And we always take, I usually take the worst case point. So you can take an average of it, but I usually take the worst case point, which is 1.8. So I'm going to select my F1 as 1.8. The range is 1.3 to 1.8. You can use 1.5. It's kind of an estimate. And if you're bothered by that, you're in the wrong major. You should go to science rather than engineering. Next up is F2. F2 is environmental factor, and it's determined by the environment. We are operating at 21 degrees Celsius. It's a clean environment, so there is no foreign matter. Okay? So F2 is what? What are these numbers really? Well, it's similar to a safety factor or an application factor. The greater it is, you are taking some margin of safety, right? Look at it. If there is a foreign matter, you use F2 of 3 to 6. Maybe it depends on what kind of, how dusty it is. But again, the dust comes into the bushings and it becomes like sandpaper, right? If you have dust in between the shaft and the bushing, you're like scratching it with sandpaper. So we are putting a bigger F2. So these Fs, you can think of it like safety margin, right? You are estimating how bad it is than theory. Okay, so 60 or lower, foreign matter, no. Just put 1, meaning no multiplication. One more thing we need to pull from tables. You're in engineering, be prepared to look up a lot of tables because industrial catalogs are full of tables. That's how they provide information. For oilless 500, the wear factor is 1207 10 to the minus 20. That's just a multiplication factor. If you look at this, a bigger wear factor means it wears harder. Okay, so a nylon, for example, will have this much wear factor. It wears faster. If you look at this formula, this is time, this is wear, and this is K. So what does a bigger K mean? A bigger K here means smaller T, less lifetime. So a bigger K means it's softer, right? A bigger K means it's softer. So you have to analyze the equation and understand what's going on. Okay, let's go. We have all the numbers. W is, wear limit is 10 to the negative 3. Length divided by 4 times 1.8 times 1.0. 1207, 10 to the negative 20. Just do everything in SI units, guys. So you'll be fine if you do everything in meters here. Okay? So we have 4.79 times 10 to the 6 seconds. Because we do everything in newtons, meters, and seconds. And this is equivalent to 1331 hours. Or how do I get the number of cycles to fail? If I know this is the time to reach failure. How many cycles will I reach that if I want that number? Multiply or divide with the RPM? Okay, so you have 200 revolution per minute. Okay, multiply with 60 minutes in a 1 hour, multiplied by 1331 hours. So you'll get 16 million revolutions.
Sir,
Yeah.
revolution, cycles, and Those are all the same, I said.
Yep. Questions on this problem? Will it fail at like 1 minute after 1,331 hours? No, it's an estimate. Again, the limit here is the wear. Will it still work? Yeah, it'll still work, but you're wearing out the bushing beyond its wear limits. So be careful. Okay? Let's do another one. With temperature rise. Okay, let's do 12-8. Can I erase this? Okay. We only have 2 hours lecture today because it's I'm sparing the 1 hour for the quiz. We'll reschedule the quiz to sometime next week. Okay. The quiz will be on shaft and rolling contact bearing.
Basically like week 1 to week 4.
Yeah, but week 1 was just introduction, right? So week 2 and week 3. Is it? No. Shaft calculation is week 3. Week 3 and week 4.
Oh, week 2? No, sir.
No, that's just design principles, right? It's hot. The problem set will be similar to what you had, well, what we discussed. So no worries. No, not plain bearing. Plain bearing will go to the next quiz. Just in case I forget again, usually, I mean, it's in the schedule, right?
Yeah.
So after 2 topics, we'll do a calculation quiz.
Oh.
So next up, after this, what is it? Can you look up the syllabus? It's gears, right? No.
Intro to power transmission.
Intro to power transmission, there is no calculation there. And then after that is gears. So gears, yes, we do have calculation. So next quiz will be plain bearing and gears. So that's how I do it. Okay, let's do this example. A bit longer here because we are asked to select a bushing size. Choose an oilless bushing. We're given the material at least. To give a maximum wear of 0.025, let's write these down. So wear, is it too small for in the back? Can you survive still? Okay. 800 hours. We have the N. We're given revolutions per second this time. It's kind of nice. Nice conversion. We have the force, 220 Newton. We are given the HCR. That's gonna come into temperature. It's a coefficient for heat. What is it? 13.3. Okay, Tmax. That's the allowed temperature up to 149 degrees Celsius, pretty hot. Static friction, 0.03. Design factor, again, this is, think of it like application factor, safety margin, they're all the same. Okay, we're about to select the bushing size. Now, we're going to do the opposite here because we're going to have to estimate the wear based on some assumptions, and then we're gonna recheck that assumption and make sure we fulfill, we're within limits, okay? So if you start to experience more and more of these kind of calculation in my class, you're gonna see that design is iterative. Iterative is a fancy word for trial and error. Okay, you try first, does it work? Yes, okay, right? So we're gonna work with the where equation, but this time, by the way, k is given there, 1207 10 to the negative 20. Again, I'm assuming this constant assumes you use all SI units, newtons, kilograms, meters, seconds. We are going to do a wear evaluation, and I'm going to rearrange the formula into L. Why do I do that? Because we're selecting size, right? I'm interested in solving for size. So if I rearrange my wear equation and put L on the left-hand side, this is what I get. And L is the length, right? We are selecting bushing size. So I'm interested in length, given all this. So that's the first thing I would like to say. The other thing is that notice my ND, and I'm doing that to basically multiply the force to be worse than it is. So ND of 2 means let's calculate it for twice the force. And the rest are standard. Now, we have a bit difficulty here for F1 and F2, because if you remember F1 and F2, what do I need in order to select my F1? What do I need to know? I mean, I have the motion, sure, but then what else? P and P. And what do they depend on? Huh? The diameter and the length, which I do not have, because I'm about to select my bushing size. So what do I do? Assume, okay? Let's assume F1 and F2 are 1. So I'm going to assume F1 and F2 are 1 to begin with. And then later I have to check whether my selected bushing will survive when the real values come in. Okay? Questions so far? So good? 1207 10 to the negative 20 times 2 times 220. Pretty lengthy equation. Hang with me. 800 hours is that much seconds. Okay? Okay? So following?
Yes.
Okay. So this ends up at 12.2 millimeters. First of all, this is theoretical, right? So there is no bushing with 12.2 millimeter length. I mean, you're gonna round it up to the next available one. But my question to you, this is the list of available bushings. So we're gonna select from this matrix. Usually industrial catalogs have this. But my question to you, is this the lower limit or the upper limit?
Lower limit.
Why? So should my L be greater than 12.2 or should it be less than 12.2? Shall I select it from the one that is less or more? And tell me your reasoning. My hint is to look at the equation. Rearrange the equation. Let's rearrange where to be on the left. So we have where will L be? Numerator or denominator?
You know, L is
If I put W here, then you got this whole thing, huh? On the top or bottom? Where do I put L? Bottom. Okay, so this is the where. My where and length of the bushing is related in this manner. So bigger L means smaller wear. Do I want smaller wear or bigger wear? Wear. So you want L to be big. And so you want L to be bigger than 12.2. Does that make sense? Okay. Same thing with time. If I rearrange time, or think of it like this, right? Time is equal to what? W times L divided by that long piece. So how is time or lifetime is related to L? Meaning, do I want high lifetime or low? High lifetime. Which means high L, long bushing, bigger area, which kind of makes sense, right? So I want L to be bigger than this threshold. Because this 12.2 is the critical point, right? Basically, 12.2, with these assumptions, will reach the wear limit at 800 hours. That's what that number means. If I select a bushing with 12.2 millimeters, assuming all that, it'll reach this wear limit in 800 hours. So if I want a minimum of 800 hours lifetime, I have to have an L bigger than 12. Okay? So that's that. Now, we did the wear calculation. One more thing we need to do is the temperature criteria, or let's call it criteria. And if I rearrange the formula, we have L, friction coefficient, ND times F times N divided by HCR delta T. Now, this is not the original formula. Original formula is delta T on the left. So, put all these in. And it's already revolution per second, so don't be mistaken there. And delta T is Tmax 149 minus the ambient temperature or the operating temperature. And we can assume it to be 20. So this is ambient or the environment temperature. The original formula for temperature is this. Now the F, I'm multiplying with ND, and I rearrange for L. Okay? And delta T is the temperature of the bushing minus the ambient temperature. Okay, so we end up with a number 38.4 millimeters. I'm going to ask you the same question. Do I want L to be greater than 38 or L to be less than 38? Tell me. Do some rearrangement of the variables. I mean, you look at this, what's the limiting parameter that is desirable? This is temperature. This is kind of a heat limitation. What do you want about this guy? High or low? Is high temperature better or low? Low. Okay? So if you want this low, what do you want L to be? Who says L should be less than 38? Who says L should be greater than 38? Okay? You move this here, L comes out, you divide by L, and so delta T decreases when L is big. And so you want this. Okay, does that make sense? So L, you want greater to be 12.2 because you want where to be less. Here, because we want delta T to be less. This is good. So we want this, right? Now, since we have these two limitations, then pretty much this is irrelevant, right? This is the governing inequality or criteria, 38.4. Now, we haven't selected our diameter. Again, you're starting to be familiar with the open answers here, right? So let's not do 38, let's do 44 and above. Any one of these should work, right? So L is 44, and then we have this selection, but only available on these dots. So any one of these four should work. How do I decide? So let's say I'm going to start with choose L 44. Okay? So I'm available, the bushings available are 25. What else? 30.
38 and 44.
38 and 44. Now, I know in reality, many times the diameter is already determined by a shaft, but this is a hypothetical design problem. So you are up for these four selections. First of all, there is the general design guide, right? The general design guide is that L over D should be somewhere between 0.5 and 2. This is just a guide. I mean, it's not black and white. It's not wrong. But it's a good place to be. So with that guideline, what can we use? I guess all of them still fits, right? But think about the equations. So kind of thinking ahead a little bit here. After we select the D, we have to do a PV limits evaluation. Right? We have P max equal to 4 over pi nd times f. You see, every time I have f, I just multiply it with nd. And then we have v pi d times n. And then we have pv, which is over dl. Okay? So, looking at that, what would be good for D? Bigger or less? So look at these. I mean, let's say L is already fixed at 44. So we have D here. High D will be good here.
Yes.
It will be bad here. It will be good here. Okay? So it's kind of dilemmatic, but let's take a random thing. How about that? Now, I'm gonna cheat here. Okay? So 4 over pi 2 times 220 0.038 0.044. This will be okay. Alright? I don't have the numbers. But if you do it here, pi times 0.038 times 5, you will end up with 0.597. Remember, there are the limits of the properties here. So, whatever that number is, that's okay. But it violates here. So, not okay. Therefore, I'm going to step down to 30. Okay? I'm going to need your help in calculation here. Okay, go ahead and calculate these for me, guys. What's my Pmax? What is it? Give me an MPa. Hmm?
0.424.
0.424 MPa.
Yes.
My limit is 24.5. I'm good. What about this?
0.47.
0.47 meters per second. Ooh, that's close, but I'm okay. So that tells me, I mean, if I want to be a bit safer, I go with 25. But hey, this might work for now. What about this? 0.33. Okay? And we are less than 1.64. We're also good. Okay, so 30 will work. So we have length 44 and diameter 30. If you do a calculation for 25, it will also work. So again, there are two options. Now, be careful, we're not done because we made some assumption early on, remember? What did we assume? F1 and F2. So now we have to go back here and reevaluate P average. My P average was F divided by DL. 0.03. What is it? My average pressure? In MPa?
0.1.
0.1.
1.
Okay? So this is definitely less than 5. So we are here. Velocity is also 330, right? So we are there. So the correct, so we're gonna check F1 1.8 and the operating temperature F2. Okay, the ambient temperature is 60 or lower and no foreign matter. So F2 is still 1. So let's recheck our wear. Okay, so 4 times 1.8 times 1, 1207. Times 5 divided by 0.044. What is it going to be? This formula is the one with F1 and F2. This one is not, so we don't have to recheck this one. What's the wear? Zero
times 10 to the minus 8.
0.125?
Times 10 to the power of negative 3.
Or is it 0.0? You might have a decimal wrong.
Oh yeah.
0.0125. Is this okay? What do you compare it with?
Smaller.
This is smaller than?
Okay.
What is W there? This is the W with this parameter. This is less than the limit. Okay, the limit was 0.025, and this is less than that. Okay, this is the wear limit. So our wear actual after we select the size and everything else, it's still less than that, so this is okay. Actually, you kind of know this is fine because if you look at the algebra, you are actually multiplying by 1.8, right? But my length is actually already 3 times, more than 3 times 12. Remember, this was the criteria for this wear. And I selected an L of 44. And 44 is much more than 12, right? So even though my factor is 1.8 or 2, this will be 24 and I'm 44. Just doing rough calculation, it'll be fine. But, you know, it's a good thing to check. Okay? Questions on this procedure? Straightforward, a bit long, but it's not that hard. So in fact, both of those will fulfill our criteria. So you can select L to be 50, I guess. You can also use 2 bushings if it's not available. Let's say you want a length of 30 times 2, like 60. You can always pick and choose these catalogs. So to sum up, you have wear criteria, temperature criteria. You also have to check these 3, and if it all checks out, then you're good. So selecting components is like that. You got different criteria coming in, and you make sure you check all of them.
Sir,
Yes.
every time there's ND, you must always multiply to reference, sir.
Yes. So design factor, you make the force multiplied. Just like in rolling contact bearing, you have the application factor. This is quite similar. You can think of it that way. Okay, I think that's good enough for plain bearings. We will have the calculation quiz sometime next week. I'm still finding the schedule, so when is your free day usually? I know it's not all the same to you, but
Wednesday.
Mereka
Theirs is Monday,
oh ya
but we're Wednesday, Friday.
Wednesday afternoon or morning?
Aiman, what about Thursday morning?
Thursday morning.
Kan kita aja jam 11 Mas.
Thursday morning. I'm
Wednesday
teaching.
full.
Iya nggak bisa 9. Iya nggak bisa.
Hah?
9 nggak bisa.
Oh,
Yeah, I'm teaching.
oh iya.
Yeah, So Wednesday, what about how is Wednesday looking
Kalian
typically?
jam berapa?
Until 4. Morning until 4. 8.
8 until
Cannot,
4.
cannot.
Tuesday.
Tuesday full.
Or in between.
Hah?
Tuesday we have 11 to
Tuesday up.
Oh, 11. I just need 1 hour.
Wednesday we have 11 to 1 Friday.
So 11 to 12.
No,
No,
12 until 1.
ours is 9 until 12.
Oh.
But if
What about Tuesday? Like,
Yes.
Sampai jam berapa?
Inner diameter.
Hah?
We have 1 hour break.
The D, inner diameter.
No,
The D is always in
until
the
like
yes.
sampai jam 3. Oh, sir. Sir,
Mhm.
Selasa habis jam 3 bisa. Kita sama-sama kosongnya.
Oke.
Selasa.
Selasa. Oh ya,
Okay. That.
Ya, after English.
Microcontroller and English kan bareng.
Iya.
Jadi after itu jam 3 bisa.
So Tuesday afternoon?
Tuesday 3 until 4.
Okay. I might not be available, but Bu Cynthia can just be here.
Sorry, so we do not own the, never mind.
Huh?
Okay.
Yes, it will be a traditional pen and paper.
The formula will be given.
Yes, all formulas will be given. So I'll give all the formulas you need. Moral support.